And then the edge distance, they actually, can you go back one slide? So you actually can define two gauge lines. You can define the edge distance of the closest hole and the second closest hole. So this is called the short edge distance, and this is called the long edge distance. So you can go to the next slide. So you can put in short and long.
It's funny they're calling edge distance, but yet it's to the center of the hole.
That's right. It's the distance from the center of the hole to the edge.
Oh, so it's the edge of the member.
The edge of the member. Yeah. The end of, there you go, thank you. And so if there is only one row of bolts, then you don't have a long edge distance. So you see some values populated in here as 0. Okay? All right. So again, as more of an example, I'm looking at 4 by 3.5 by 1/4. I can see by this dimension that the holes are connected on the short leg, the 3.5-inch leg. So it is connected on the short leg, and then I don't have values here because we get into the scanning and clarity of dimensions. But when I would input these values, this would be the end distance, this is the spacing, this is the short edge distance, this is the long edge distance, because here's the heel of your angle. So it's always measured from the end and the edge. That's how you input these values, which is unfortunate because the short edge distance is never dimensioned on the tower drawing, on a detail drawing. They dimension everything from the heel, so you got to do math, right? 1 1/4 is 2.5. 3.5 minus 2.5 is 1. So my short edge distance is 1 inch. And then I know my gauge is 1 1/4, so my long edge distance is 2 1/4. You got to do math to get it. It's a pain. That would be one thing I wish PLS would do, is actually specify the distances from the heel, because that's what you see on all the drawings, but that's not what they do. So this is what I was talking about with reference to the code. Okay? The code does not tell us strength. It tells us distances. So the end distance, 1.3 times the bolt diameter. That's a minimum. Or the thickness of the member plus the diameter of the member divided by 2. You got to meet that minimum. Or there is one that's somewhat tied to load. So it's basically 1.2 times the load in the bolt divided by the rupture strength of the material times the thickness. But that's essentially the 3 equations that control end distance. How you must meet these end distances if you're designing new towers. Again, this is going to be this kind of interpretation deal. Center to center hole spacing. It's essentially this equation plus half of a bolt diameter. So the idea is that if my end distance here is E to the center. So if that's my end distance to the center, then I want to provide this at minimum the same distance to the edge of this hole plus 0.6 bolt diameters gets me roughly to the center of the hole, right? So that's where this comes from. And then here is historically has always been used successfully. Whatever the minimum of these 3 are, 85% of that is how close you can get to the edge. Not the end, but the edge, right? So this is what the code says we have to meet.
Has that code been around a long time?
Well, all of those were part of the manual of practice, which was best practices for how to define bolts and connections.
So did you find that typically that was being adhered to as on a lot of these or not?
Yeah, I feel like in most cases, if you get into really, really old towers, the end distance might be shorter than what's typical. But a lot of time, like on all your your drawings from the 60s and 70s at least, there's a standard end distance, 1 1/4 inches or something along those lines. That meets these. Okay. It all meets these. So this is what PLS Tower has to say about rupture. The rupture checks are optional. Rupture is a catch-all for various ways in which a connection can fail under member tension, excluding net section, or the occurrence of... Rupture failures can be longitudinal wedge tearing at the end of the member, cracks between holes in the edge of the member, block shear, insufficient bearing strength of bolt. So all this is fall under rupture, right? They capture all of this. What they do is they say they have a simplified interpretation of the ASCE spec, right? Because ASCE doesn't give you rupture strength. It gives you minimums that you have to meet. So Tower has taken it upon themselves to turn those requirements into a strength calculation that is simplified. Essentially, they're looking at this RBSH as block shear. We're going to throw that out for a minute. And the R distance is a rupture strength based off of all the distances that we've been talking about. So I'm going to focus first on here. R distance is a way to check for requirements for end, edge, and spacing distances, and the other one is for block shear. Okay? I have a note here that's something to remember that I'm going to come back and get to you. In Tower, a strength is calculated for the entire connection based on the single bolt with the smallest end, edge, and spacing distance. So basically, they find the worst. They find the one bolt that least meets the end, spacing, and edge distances, and they use that to say that is the strength of this bolt, and then we multiply that by the number of bolts, and that's our rupture strength. That's very different than what AISC does. So you need to be aware of that. So all bolts, assume to have the same strength. So what do they have? What they do is this equation should look very familiar to that top equation for end distance. They've rearranged it so that the, actually, can you go back like 5? Oh, and go to the next slide. Yeah, here we go. So if they rearrange this equation for P, they get this, right? Where you have FU over 1.5 or 1.2 times the thickness times E. So you can go back one slide.
Is that FU ultimate strength?
Yeah, the ultimate strength of the material. So what they've done, right, is you've got FU over 1.2 times the thickness times, we're going to call it distance for now. And then they've got basically the number of bolts, the number of bearing areas. So if you had a bolt in double shear, you'd have 2 bearing areas on either side of your member, times basically alpha, which is a reduction factor. Okay? And hopefully you'll be able to see how all this comes together. Your distance is the minimum of your end distance, your spacing minus 0.6 of the bolt diameter, or your edge distance divided by 0.85. So what they essentially did was take all those different minimum distances, and they flipped them to be essentially equivalent to the end distance, and then you calculate the minimums of all of them. Whatever the minimum of all of them is, that goes into this equation. So if my end distance is 1 inch, my spacing minus 0.6 of the bolt diameter is 2 inches, and my edge distance divided by 0.85 is 1.5, then it takes my end distance of 1 inch and feeds it into this equation. And this is the rupture strength per bolt, and then they multiply by the number of bolts, the number of bearing areas, and a strength factor. Okay? So that satisfies almost everything. The number of bearing areas is automatically calculated in your sections, in your member properties table where you do the leg size and the thickness and the W/T ratios. You will specify whether there's one angle or two angles in the section. Is it a single angle or a double angle? Depending on that input, it will determine basically your number of bearing.
I'm kind of confused by number of bearings. Is that like related to the bolt? Is it kind of related to the bearing stuff we were doing on the bolt before, or no?
Yeah, it's kind of like bolt shear, essentially. So if I had a double angle, basically in bolt shear, if I had one bolt in double shear, there's 2 shear planes. So the number of shear planes would be 2. Here, in that same case, that bolt is going to be bearing on, or it's going to have bearing on 2 different pieces of that member, of that double angle.
You have 2 bearing?
Yeah, so like if I had a double angle, and then I had a plate in here, and I have a bolt that connects them here, and like the end of this double angle looks like this, then essentially, right, if I was worried about the rupture at the end of this, the single bolt would have to rupture through two angles to fail.
You're just spreading a load over, over two angles. Instead of
okay.
So in 99% of the cases, you're dealing with single angles, so the number of bearing areas is 1.
Okay.
Right? The last thing they do is, how do you handle the fact that can you go down one more? So essentially, everything I've talked about so far incorporates this equation, and this equation, right? In a simplified conservative manner. So what do they do if you don't meet these two? Can you go back? They basically, this alpha is like a penalty function. So they basically divide your end distance by 1.3 times your bolt diameter, and if that value is less than 1, then they let's say that it's 90%, then they decrement your rupture strength by that penalty function. And they do the same thing with this kind of thickness requirement. So you can go to the next one. So in other words, my end distance based off load is based off this equation. But if I haven't met this stipulation, then they basically decrement your load by a ratio. I understand how they got to that. I understand why they do it. It's just not perfect way of.
I think that PLS comes up with this stuff.
I mean, to be fair, that would be if you were to ask me how to incorporate this in a simple way, I would probably do something similar to what they did. They were kind of put into a box because this code doesn't say, here's how you calculate the rupture strength of a connection. It says, here's the end distances you have to meet, but there's no way it gives you a real strength. Or it gives you all these different rules of thumb that aren't tied to load. So how do you come up with something that is tied to load but then also accounts for these rules of thumb? So that's what they're trying to do. It's really difficult for them to do it in any better way.
At least it's tied to the code this way, right? If they were to come up with their own equations,
right,
then someone would be asking a lot more questions.
Okay, so you can go to the next slide. Let me see what it is. So a couple of key observations of this approach, right? Number one is that the total rupture strength is penalized even if a single bolt has poor spacing. So, let's say that all these 3 bolts meet all my requirements that I need, but there's this rogue bolt down here that is too close to the edge. What Tower's going to potentially do, right, is it's going to say, well, if this is too close to the edge, then the rupture strength has got to come way down. And then it applies that strength to all 4 bolts. And you could actually have a case where this connection comes up in the program as being calculated as weaker than this connection. Because even though I have less bolts, I don't have to worry about this penalty because it's too close to an edge. Right? So this is an observation of something that can happen. The next one. Right. So go to the next one. Yeah. So what I'm saying here is that, like, let's say that in fact I did have something where like this crack developed right here, but the remaining 3 bolts might still hold, right? So you potentially are calculating to limit the potential for this crack to happen, but is the crack really going to happen at the low level of load that you're calculating, or as these things load up, might they all actually carry a little bit of a different, where the ones with more spacing and edge distances hold more load from a rupture standpoint. And I bring that up because, the next one. And I bring that up because this is very different than how I learned to design connections based off the steel manual. What the steel manual says to do is if I had a connection and I had, let's say, 2 bolts, I could actually calculate what they call the bearing and tear out strength of this bolt. And that would look at this bearing failure and kind of this tear out failure. And I could assign, a strength to that. And then I could look at the bearing and tear out value of this second bolt. And that might be different than the first bolt. It might be more. And AISC basically says you can add those two together, and that will give you a representation of the rupture capacity of the connection. Right? So the approach is different. They allow you to look at each bolt individually and calculate a rupture strength per bolt. The code doesn't tell you what to do. And Tower essentially is looking at a conservative, simplified model that doesn't do that.
I'm still confused a little bit between rupture and the bearing.
Yeah.
So is rupture kind of more like a shear failure of that material?
That's right.
In that versus bearing just kind of like more of a deflection of that, or
right. So in an extreme case, if I had a bolt way out here really far from the end,
yeah,
and let's say that the bolt shear is not a problem.
Yeah.
So what's going to happen is I'm going to deform the material. I'm going to ovalize this hole. The base material is going to ovalize and kind of bear and fail.
Yeah.
So that's the bearing failure calculation. The rupture failure is more about basically a crack developing between the hole and the end of the member,
Okay.
or a crack developing between two adjacent holes,
Yeah.
or a crack developing, to the edge of a member. So that's the different kind of mechanism that we're talking about.
Okay.
But like I said, AISC, when I learned to design connections in school, they lumped bearing and tear out together. Like you looked at the bearing capacity of a bolt, the tear out capacity of a bolt, and you took the minimum of the two, and that was the strength of that individual bolt. What the program does is it looks at the total bearing connection and gives you a strength. And then it gives you the rupture connection and gives you a strength.
Yeah.
So it's just different. It's
Yeah.
different. It's not, I can't say that it's incorrect. It's simple. It's a simplified method of what to meet these minimum spacings is what they're doing.
When we're looking at the bolt that is close to the edge,
Yeah.
Does it take into account the fact that will rupture before the other ones do?
I mean, what it essentially is doing is it's saying that you're calculating a theoretical load in this bolt that'll cause this crack to form. And then what it also says is that it's assuming that all the bolts in the connection are going to share load equally. So if this is limited to 5 kips and we have 3 bolts in our connection, then if I have 15 kips of demand, then I have 5 kips in each bolt, and then if this has 5 kips, it's going to crack. That's the assumption they're making, right? And all I'm saying is that I can't argue with that as being wrong. I think that is a simplified assumption that's consistent with what we do when we calculate bolt shear. We say, what's the total demand divided by the number of bolts? That's the bolt shear that we have. Right, we do that in bearing, right? As we say, what's the bearing strength? How many bolts do we have? I showed you a picture of the bearing was more dramatic on the end bolt and virtually nothing at the, but that's just not the design methodology that we've adopted to assign a strength, right? And what all I'm doing to point out is that the methodology that Tower uses is different than other ways that you can calculate rupture strength of connections, right? Other people, other industries will actually say, well, this is limited to 5 kips, but this might be 7 kips, and this might be 10 kips. And it'll say for this whole thing to fail and rupture, you need to eclipse all of that load. Now, that argument could also be different. That argument's not consistent with the same load in all the bolts for bolt shear. So it's kind of about what methodology do we assume, simple methodology, simple that we can calculate relatively easily and get a number. But again, the challenge is that you can run into a case where you're having rupture failures, but it's possible that you could use another method that is recognized by other steel industries as being valid, and get a stronger strength. And because this code doesn't actually tell you how to calculate a rupture strength, it just gives you minimum spacings. You're not violating, if you meet the minimum spacings, you're not violating this code in any way of calculating it that way.
So if the towers have typically been designed to meet that minimum code, why is rupture ever an issue then on the towers?
That's a good question. What we typically find is that rupture ends up being a problem in connections that have single bolts, or in block shear, which is what we haven't talked about. So, I mean, generally what the rupture strength is doing, and you got to think about it from a designer's perspective. If you were designing a tower, if you were trying to detail a tower, the rupture strength would be a way to flag where you might not be meeting code spacings. If I were to analyze older towers, my experience is that when you get into more than 2 bolts, rupture strength is hardly ever, rupture in this way is hardly ever going to control, if ever. What I have seen is block shear control, which is classified by tower as a rupture failure. They never looked at block shear when they didn't do that 30, 40 years ago. So a lot of times when we're reinforcing for rupture, what we're really doing is trying to fix a block shear problem. Okay?
Also, if the load goes up too, right? I mean, there's a couple.
Oh, that's right.
Couple of the parameters on rupture are load based. So if the load number goes up, reconductoring or whatever.
Right. So that's actually a really great point. One of the minimum edge distances was based off of what the demand was per analysis. I reconductor and my demand goes up, all of a sudden that rupture strength, that end distance may not meet anymore because I based it off of the original design load and my loads went up. So that's that's a good point. Yeah, so I guess what I'm saying here is if you have a rupture failure, check that block shear is or isn't controlling. If it's not controlling, then it's possible that tower has calculated a conservative connection strength. And what I would recommend is if you wanted to look at it, can you go back up, keep going, one more. If you wanted to calculate a different rupture strength, you could use this kind of approach from PLS, and just for every individual bolt, you calculate its distance, so the minimum of these 3 values, and plug it into this equation for each individual bolt and sum them up, right? And that would be a way to get another calculated rupture strength. But for the most part, we don't see this with 3, 4, 5 bolt connections. So you're very rarely in a situation where you're worried about that. Okay. Next one. So what are the values that control rupture? Number of bolts, your edge distances, your end distance, your bolt spacing, right? All the things we've been talking about. This is where, when you're not putting this information in, you may not be capturing these kinds of things. All right. So the other rupture in tower is block shear. Block shear is a combined tension and shear failure mode where basically a block of the angle material breaks away from the rest of the member. So what I mean by that is, like, you can see where I can shear across this plane and have a tension failure here, and if I lose that material, this member is no longer connected to the gusset plate, right? It completely fails away. The failure block must enclose all the bolts. You can't have any bolts that still connect the member to the rest of the tower. Multiple failure patterns are possible, but usually the controlling condition is pretty clear. So you go to the next one. What's our code say about this? Pretty simple. You have to calculate a shear area, so the area of the member in shear, multiplied by a ultimate shear strength, which is 60% of the ultimate tensile strength. Very common conversion between tension and shear. And then the tension area times the yield strength. So the idea is that you're going to basically, if I looked at this as the block shear plane here, I'm going to have a yielding failure on this area and like a shear rupture along along this area. So my shear area is A plus 2B times the thickness, and the tension area is this C value times the thickness. Okay. So some examples: single angle, right? Red is in shear, blue is in tension. This is a double angle. So, or this is like a, I'm sorry, not a double angle. This is like a tower leg. So I'm looking at two legs of a tower. And so you would actually need to block shear through both ends of that, both sides of that leg angle. Single row, two legs. Okay. If I had a double row of bolts, then I have to look at a pattern, right? It has to eclipse all bolts. So if I break through here, then this white member can pull away. You could also theoretically block shear through the middle, but by inspection, right, is that this is common between both, and this little area and this large area, it's very clear that this is going to be the controlling condition. So if you have a simple connection of a single row of bolts on one leg, only a single row of bolts on one leg, Tower will automatically calculate your block shear for you. Here's the equation as it's listed in the Tower manual. It's the same equation I showed you a couple of slides earlier from the code. And again, when members are connected on one leg for a single line of connectors, Tower will automatically calculate this for you.
How does it know that? How does it know what that pattern is?
If right, so part of my inputs, if I have a single row of bolts, is I have to input the end distance, the spacing, and the edge distance, and the number of bolts. And so from that information, Tower can make an assumption as to essentially, it uses the edge distance to get the tensile area, the end distance and the spacings to get the shear area, and it can calculate that for you automatically. So
I'm struggling with, there's like these three different failures that can occur, and it seems like it's hard to believe that all three of them could possibly occur. It seems like one of them is going to be like always typically the controlling failure. And
it depends on bolt pattern. So, for instance, if I had a member where I had one bolt, but it was kind of close to the heel of the angle, then potentially the rupture strength to the end of the member would control. Whereas if I had that same connection, but the bolt was down here, maybe it's this little block shear that controls. Or, if I had, this is a very common one, I have two bolts in a connection, is that, maybe I meet all my spacings, but I've got this block shear failure. So,
why would block shear occur versus rupture? Or why would rupture occur versus block shear?
So essentially it's all about our edge distances and our spacings. I guess part of it is that I can't give you a rule of thumb to say which one is going to always control over another one. I can just kind of say that we're checking all of them and we're going to find which one the minimum is what we're doing. And which one controls is, I could essentially, if I had this bolt pattern, but I put it on a longer leg, then all of a sudden my rupture strength hasn't changed, but my block shear strength has gone up. Right?
Yeah.
So, I could have the same bolt pattern with the same distance from the heel, but if the if the leg that it's on is a half an inch longer, then that might be all you need to make block shear no longer controlling. So you got to check them all.
Isn't bearing always going to happen first before it's shear, before you have rupture or block shear?
It depends on the thickness of the angle. I guess that's I can't tell you that any of them is going to dominate over the others. I don't have enough experience in this to look at it and say, I can say generally bearing is not controlling. I can tell you that. It's very rare that I've seen bearing controlling over anything else. But you could put weak bolts in here and it's all bolt shear.
Yeah.
Right? Or I could put, or you could put, it could be weak bolts, but it's bolt shear and block shear. Right? I mean, it's every case is unique, unfortunately. What I'll say is that for a lot of the stuff that we're talking about, again, is mostly for connections that have one or two holes. So like legs with those big lap splices and butt splices, none of this is a problem.
I see what Joe's saying about it looks in a way like bearing would potentially control, but I mean, all the different factors, like you think, like you just make the holes bigger, well then you have a larger bearing surface, but then a smaller shear surface and tensile surface. So I don't know, it's all give and take.
I think it all is a function of the strength of the material too. And
that's true. Absolutely.
It's toughness and it's other things in there too to that level. I mean.
Well, and that's the other thing is it's part of it is a ratio of yield strength to rupture strength. Because rupture is part of the bearing strength, it's part of the block shear strength, but yield strength is part of this. Yeah,
because this is all.
Yield strength is part of the net section.
Yielding stuff. Yielding would be the bearing.
Right.
Failure. This is all ultimate strength stuff.
So, I mean, the best I can tell you is that if we wanted to sit down and systematically look at a bunch of different scenarios, you might be able to actually kind of rule out and say, hey, rupture, tear out is only, or the tear out part of rupture will only control under very specific conditions, or bolt bearing may only control under very specific conditions. That's very possible. I don't know. I haven't done that analysis, and so it's hard for me to single out and tell you which one of these really matter and which ones don't.
Can you model a tower without any bolt connection stuff at all?
Can you? Sure.
How does it know it's connected then?
So, essentially everything we did this morning is all you need to get demand in every member, right? So
you're just defining a joint and defining a member.
That's right, and so they're connected, right?
But now we're basically defining the details of that member
to get its strength,
capacity,
to strength, right? And so what we're trying to do is check all of these strength limit states, these capacities that are defined by the code within the program. And so the program is responding to the requirements of this document.
Yeah, okay.
You know what I mean? And so even if you could sit down and systematically say, well, bearing's never going to control, this document says that you got to check it. And so it's pertinent on your tool to provide that check. So that's kind of why it is the way it is. I said that the program will automatically do a block shear calculation for a single row of bolts on one leg. If you don't have that situation, meaning essentially what that means is that my connected leg is both, or I have a long edge distance, right? Because essentially what the program is doing is if I say that I have if I only put in a short edge distance and two bolts, then it basically assumes that both bolts are on that short edge distance. If I put a long edge distance in and two bolts, it's going to assume one bolt is on that short edge distance and one's on the long edge distance. So if I...
They need you to sign.
So for like this connection where I say there's a long edge distance, or this connection that says I'm connected on both legs, Tower is not going to do a block shear calc for you automatically. It's not going to. Up until 3 or 4 years ago, you basically had to try to trick the program again with like spacing. So you'd be putting in fake spacings to try to get it to do a block shear calc for you. Since then, they've added these two columns where you can manually input a shear path length and the tension path length to be used in the block shear calc. So this is another instance like net section where you kind of got to do a little bit of calcs on the outside of the program to get proper inputs. so that it'll do the block shear calc for you. This is not the best example because I think that the tower that I used to develop this screenshot was developed before these columns were added, so we actually don't have these values populated in this table. But normally, if you saw a value here or you saw both, you want to see values populated in this table. I know some utilities that don't worry about these distances for legs, these lap splices and legs, these butt splices and legs. Block shear is not going to control an 8, 9, 10 bolt connection in a leg. So it's really more critical on all the other members other than the legs. All right. So when we use the alternative calculation, then basically what we're left with doing is we're required to calculate the length of the shear length and the tension length. So we kept talking about shear areas and tension areas. The input is length. So tower can multiply by thickness. So it wants to know what is the length of this red line, excluding holes, so with the holes already subtracted, and the length of the blue line with the holes removed. That's what you're going to put into those two columns on the right, and then it'll calculate this block shear calculation for you. This isn't always perfectly simple, right? What do you do in any of these, right? How do you handle these situations? I think we're going to talk about it a little bit, but I'll kind of go over it in general. Something like this is a judgment call. And what I mean by that is, nobody defines for us whether you should look at this as being a tension failure or a shear failure. If it's like a standard and, 45 degrees or so, then generally what we'll do is use the S squared over 4G approximation to calculate this as a tension length and assume a tension failure. If it's much more elongated like this, we'll assume it is a shear failure. And so you can calculate this length and then add that to your shear path. But that's kind of a judgment call. I mean, there's no hard defined rules on how to do it, right? Here we have the same problem we had with our bolt staggers. Is what is longer, this length or this plus this in tension, all right? So you can run into some more complicated situations. I'll give you an example for block shear. So I'm looking at the end of this. I'm looking at both ends of this member. So what do I want to do? I want to decide which one is controlling in block shear. It looks like the end distance here is pretty similar, right? This bolt is 2 inches from the heel. This one is a little bit more than 2 inches from the heel. It's 1 1/4 plus 7/8. And my bolt spacings over here are smaller than my bolt spacings over here. So when I just look at this, I can see that this end of the member is going to be the weakest in block shear. I can do a couple of things. Again, simplified or a little bit more refined to get different block shear strengths. So one of the things I could do in tower here is I could assume that these two bolts were actually down here on this gauge line. So my block shear would be through here. So I wouldn't input like a long edge distance. And I could also pick the smaller of the two spacings or an average spacing. And I could put that in as the spacing in PLS tower. So if I did that, tower would then automatically calculate a block shear strength for me. So you could do that, right? I could say, I'm going to give a single short edge distance of 7/8, which is the distance from here to here. And I'm going to give a bolt spacing of 1 11/16, which is the smaller of these two spacings. Tower will automatically calculate a conservative value of 24.4 kips. Now, if you did that, and you looked at what your shear capacity was for bolt shear, and it was 30 kips, or it was 20 kips, then this is probably okay, right? Because it's not the limiting value. I could hand calculate a more precise value, which I think I do on the next page, on the next sheet. Okay. So I could essentially, I'm going to do the same thing, but I'm going to be a little bit different. I'm again going to assume that both of these are down here, but now I'm going to calculate my own shear path. So it's going to be 1 inches on the end. So that's the distance from the end to the center of this bolt. 1 7/8 of an inch from bolt to bolt. 1 11/16 from bolt to bolt. I'm not going to add anything for the diagonal. I'm just going to be conservative. And then I'm going to subtract 2.5 holes. Right? 1 hole, 2 holes, and a half a hole. And I get 2.6875. I can input that into that column on the right in my member table. My tension path is essentially what? It's 3 inches. It's a 3 by 3 angle. 3 inches minus 1 1/4 minus 7/8. So it's basically what's left is 7/8. So that's this distance minus 1/2 of a hole. And I get 1/2 of an inch. And if I take those values and drop it into the equation, I'm going to get a larger value, right? A little bit of a larger value. Okay?
So,
yeah.
Do you typically do that by hand and then compare that, like you said, to the bolt and then just ignore that? Or?
I mean, what we typically do is calculate these lengths by hand and just drop them into the program. And by hand, I mean, again, we do this enough that we've taken the time to develop a spreadsheet to get these numbers for us. So we kind of define the different bolt spacings and things. And
how are you entering this different from the other stuff? You're saying because it combines the rupture and this together. How are you?
So what I'm trying to do is populate. Can you go back to the member table? I'm trying to get numbers to populate this column.
Yeah. Okay.
Right?
Yeah.
And so that's what my example calc was numbers to populate this column. Tower will use this to calculate block shear. It'll use all of this to calculate the other rupture strength. And then it'll take the minimum of those two and that'll report it as the rupture strength, right? Big pain in the butt. So I think I had an example. So in this one, I think what I'm going to do, I'm going to say, well, number one, I'm going to say leg splices don't typically control and block shear. But I do have a leg here. But let me see what do I have my hand calc example? Let me see. Oh yeah, it's a different one. All right. So I've come up with like another demonstration example for you guys to kind of try to maybe hammer home exactly the calculations that we're trying to do here. I'm looking at the block shear calc, which looks like this. It's got a nice angle on the front. So, oh yeah, I didn't. Yeah, you know what? I didn't even talk about that one. I can come back to that. So this actually comes from the DP tower. This is one of the diagonals on the DP tower, and the idea is, what do we put in as the shear path and tension path in our rupture check? And so I can see that my connections are symmetric. So I can look at either end, and in general, it's a 2.5 by 2 by 1/4, but the 2.5 is in this direction. My shear path is going to be the total length minus 1.5 holes. So it's 1 inch plus 1 5/8 plus 1 5/8 minus 1.5 hole diameters, which is 1 3/4. And so my shear path length is 3 1/4, 3 1/8, and that excludes the holes. For my tension path, I'm going to look at two options, number 1 and number 2. Okay, so for number 1, basically, can you scroll back up to the top for a second? I'm going to say that this distance from this bolt to the end is 2.5 minus 1 inch. It's 1.5 inches, but I've written it down as 2.5 inches minus 1 inch, so that's that length, minus 1/2 of a hole gives me 1 1/8 inch here. Okay. The other option is this. And essentially, the way that you do the stagger is you look at the perpendicular distance. And so I'm saying it's this 1.5 inches minus 1.5 holes, because I'm cutting through 1.5 holes. And then I'm adding back s squared over 4g to account for this extra length. Same thing we did for net section. So my s is my spacing, 1 5/8. My gauge is 5/8. So you can scroll down. And so I go through that calculation here. And I basically get 1.43 inches. So the tension area of the second one is more, tension length. So that doesn't control. Path 1 controls. So those are my lengths. Those would be the values that I would put into tower. What tower is going to do behind the scenes when it calculates, if I assume an A36 material, is here's my general equation. My shear area is the path, shear path times the thickness. If I have a 1/4 inch angle, then I multiply my shear path length times my thickness. I get a shear area. I can do the same thing for my tension area. So shear area and tension area. And I can drop those into this equation with the appropriate material values. And you basically can see the equation through. 0.6 times the F sub U for shear, F sub Y for tension, and I get 37 kips of block shear. All right, so that's an example of the overall calculation. For what you want to put into tower, is that it, Chris? I think it is. What you want to put into tower would be these values, right? And if you put these values into tower with a A36 material, it's going to come up with the same number.
And then it's comparing. So when it's how it's using that number then is it's looking at that versus the loads that's being applied.
Right.
And it's comparing the loads being applied to both that, the bearing,
the bolt shear, yep,
and the rupture, and just seeing
net section, all of it.
Net section, and it's like whatever's the limiting factor,
right,
could show that thing's over.
Right. So the member is going to get a usage. If it's 103%, it means that the demand is 103% more than the minimum capacity of those.
Yeah.
The least capacity.
Okay.
Yeah. So I also have in your hand calcs more information on the rupture. And maybe I should have gone over this a little bit more earlier. It might have answered some questions. But part of this is I'm going to try to define where some of these different things came from if I haven't done it already. Again, our general definitions of end spacing, short edge distance, and long edge distance as it's found in PLS tower. I mentioned that there's this 1.3D as an end distance limitation. That is basically a historical success thing. Somebody a long time ago said, this seems like a good number I'm going to use as an end distance, and they've had no problems with it. So it got incorporated into the standard. That's where it came from. And they tell you that in the commentary.
They thought of testing too, I'm sure.
Yeah, I'm sure, right.
Yeah.
Essentially, this limit is about fabrication. So if the end distance is less than your thickness of your material, then you have problems when you punch the hole. So if you have a 1/2 inch thick material and you're trying to get it so that the edge of the hole is a 1/2 inch from the edge of the member, you have problems doing that. So this is kind of a problem for punching. And then I'm going to talk about, again, the derivation of where this end distance came from. So you can keep going. So I'm going to talk about the development of, again, where does this equation come from? I'm going to relate it to basically a tear-out failure. So if this member were to tear out on the end, then I could look at it as basically, I could look at it in a different way. I could say that I could take, if the end distance was from the center of the hole, I could say I've got I've got the end distance minus half of the bolt diameter. That's going to get me the distance from the approximate distance from the edge of the hole to the end of the member. I could say that I've got the thickness of the member times 2 failure surfaces, and then I've got like a limiting shear stress. So that's like a shear failure across both of those planes. That's a different way to think about this tear out. And if I approximate the shear strength as 70% of the ultimate tensile strength, I've used 60 before. For this example, 70% works out to be a better approximation, and that value can be anywhere from 0.6 to usually 0.7. Then I get an equation that relates essentially tear out to rupture strength. So I can scroll down. I can look at the bearing strength of that same connection as essentially some kind of allowable bearing stress times the thickness of the material times the diameter of the bolt. So some kind of allowable bearing stress. So I want to calculate an end distance such that bearing controls. So this kind of gets back to you, right? If I meet all these end distances, what's going to control, bearing or tear out? So the equation was kind of developed with the idea that bearing would control. So if I take this equation here and I set it equal to the equation from above, and I do that here, then I can basically reformulate these two equations, and I get this relationship for what is end distance divided by diameter. So end distance divided by diameter is 1/2 plus 0.715 times the bearing strength divided by the rupture strength of the material. Okay, I get this relationship. Scroll down. Why that's important. This is basically a plot of testing data of connections that fail in failure of connections. And what we're looking at here is the end distance divided by the diameter. And we're looking at basically the ratio of bearing stress to, I think, the failure load. And the theoretical equation that I derived above using different base principles is basically this dark line. So I can see that theoretical bearing tear out capacity, right? If I specify so that bearing controls over tear out, what you find is that relationship very well matches the data. One of the things that the tower folks did was they looked at this and they said, but you know what? If I take a simplified approach and say that the end distance divided by the bolt diameter is simply related to the bearing capacity divided by F sub u, right? Then I get another line that also very nearly matches the data, right? It's a good approximation. So they kind of adopted this simplified approximation to get their strength calculations. And then essentially what they did was they multiplied this line by 1.2 for conservatism. So in other words, the idea is if I increase my required end distance relative to diameter, then my design line is going to be above the actual capacity. It's going to be on the conservative side of the data. What I will also show here is this is the design space that we designed to in ASCE, where I've got my 1.3 is like my limiting bottom end distance. This is the section that's controlled by that 1.2 equation, and then my bearing capacity is limited by 1.5 times F sub u. So this is where essentially what we're finding is that our designs are going to typically be, somewhere in this area, which is kind of and in this plot above the data is all conservative. So it's just a little bit more of an explanation. And so that's what I did, right? This is that simplified line that I showed which is the basis of equation 451. Applying a factor of 1.2 to account for uncertainty gives this equation for essentially the end distance and related to the bearing stress. If we know that the bearing stress is essentially the load divided by the diameter times the thickness, then you can substitute this in here, and what you end up with is essentially our design equation in the code. So that's kind of where it came from. You can do the same thing for spacing. It's just that I'm going to substitute, right? Is that my E is this value, and I'm going to substitute E for S, where I basically I need to add 1/2 of a bolt diameter to get to kind of the equivalent spacing, right? And I don't have any data for the edge distance. So that might have been more confusing than it was worth, but I provided it to you, so I wanted to go over it. Certainly you can, if you're interested, you can study it a little more too, and see if more questions arise. I'll be happy to answer them. So let's see, where am I on rupture?
What I was about to go over is, Tower calls rupture and block shear. They just call both of it rupture, which he's said multiple times. He's going to go over how you find the differences in the data. But what you're talking about is, you're finding the minimum of the net section, the block shear, the rupture, the bearing, right? All of those things, finding the minimum, and that's your capacity.
Yeah.
Tower gives you the capacity for the bearing, the net section,
the shear,
right? All those things, but then it just gives you one value for a rupture, and that rupture includes rupture and block shear.
The other rupture limit states in block shear.
Right. So, unfortunately, it gets very confusing, which is what Adam's going to kind of try to explain. How do you find what's controlling? Is it block shear, or is it true rupture?
Okay.
So the program does provide some help. There's 3 locations that define this. At the top of your member connectivity table, so where you input all your member properties, it will actually tell you the member will not be checked for block shear since more than one gauge line exists. And so the idea here is that there's more than one gauge line, but they have an input shear and tension path lengths. So it'll throw a warning to say, block shear is not being checked for this member. Be aware of that. That same warning will show up on your output report. So this is like a result. When you run an analysis, you get a list of warnings, and it will give that same warning at the beginning of your output reports. The last is, and we're going to get into capacities and overrides a little bit more tomorrow when we talk about reinforcements, but once you've created a model, you can actually look at the capacity of every member based off of all these limit states. So you can go do that. And so there's a table in the program that will list all the different, the net section capacity, the rupture capacity. It'll show you the controlling capacity. It'll list them all for every member. So you can just go look that up if you're interested. But the idea here is that, here's the single rupture capacity, and it will tell you that the rupture capacity for this member is controlled by the distance rupture, not the block shear rupture. Okay. I do have a note that say you got to be a little careful. One of the issues with the way that they implement this is it only displays this check when block shear is calculated by tower, and it does not control. So in any other case where tower is not automatically checking block shear, it's not necessarily going to give you this warning. So it's not a perfect place to find this kind of stuff, but you're kind of able to at least get a feeling for looking up and trying to figure out which limit state controls. To me, the easiest thing is you go into the member tables and you start adjusting like the shear and tension path values, and you see if the rupture strength changes. If you increase your shear path and the rupture strength doesn't change, then it's the other one that's controlling. All right? All right. So, general summary. Good